Hello! In this video, we will learn how to use recurrent neural networks to estimate, or better to say, to reproduce input-output behavior of dynamical systems. We are going to use Keras and TensorFlow Python machine learning libraries. Here's a brief lecture outline. First, I'm going to give you some background information on system identification, parameter estimation, and I'm going to relate Statespace models with recurrent neural networks. Then I'm going to explain the Python codes I used to estimate the models, and finally I'm going to present you numerical results. I'm going to use a simple example of a mass and spring system. So why I'm using a mass and spring system? Well, mass and spring systems are prototypical models of a large variety of physical systems. They are described by second-order differential equations having the following form, where F is a force, so control force, and X is displacement from the equilibrium point. So by testing machine learning algorithms on such a simple system, you can obtain some conclusions that might be useful for more complex systems. And the codes I'm going to present can easily be generalized to more complex models. Here, this graph represents final results of using recurrent neural networks to estimate a model of a mass and spring system, and these results are obtained for increased number of internal nodes of your neural networks, and this will be one of our last slides in this lecture. Before I start, I would like to say that I have created a post that describes everything that I will say in this video. This post contains equations, contains basic descriptions of recurrent neural networks. I present a numerical example. I explain the codes. Then I present some results, and finally I give some conclusions and some future directions for using recurrent neural networks for estimating models of dynamical systems. A link to this post is given in description below. First, we give the problem formulation. What you can see over here is a mass spring damper system. As I mentioned previously, mass spring damper systems are prototypical models of a large variety of dynamical systems. For example, what you can see over here is a shock absorber in your car. So if this is your wheel, if this is the wheel of the car, right, you have a shock absorber that connects the wheel and the frame of the car. So when you hit a pothole driving, right, this shock absorber should ensure that you sitting in the car do not oscillate. So it should absorb the shocks. Now, what you can see here is actually a spring and a damper, and this is nothing less than our spring mass damper system. Now, we will be interested in finding a relation, a mathematical relation between the force acting on the mass m and the displacement of the mass. So let the displacement be denoted by d. So we want to find a mathematical relation relating force and displacement. Now, one of the approaches is to use the second Newton's law. So we can write down the equation originating from the second Newton's law. So the ordinary differential equation originating from the second Newton's law has the following form. Second derivative of displacement plus the damping constant times the displacement, the first derivative of the displacement, plus the spring constant times the displacement should be equal to some constant times the force. Now, I will stop for a moment and I will let you think, what is the main problem with such an approach? Why this approach might fail in practice? Well, if you know the answer, congratulations. You have a basic insight that an engineer or a physicist should have. The answer is that in practice, we often do not know the precise values of the constants Kd, Ks, and K defining the mathematical model. These constants might be completely unknown, or we might know them up to certain uncertainty. Sounds funny, certain uncertainty, right? And we will not be able to accurately predict the behavior of the system, actually the behavior of the model. So if we know the function of the force, we should be able to predict the function of the displacement. Well, if we don't know accurately Kd, Ks, and K, our prediction will be inaccurate. To overcome the drawbacks of the second Newton's law approach, or in literature this approach is called the first principle approach, we will use estimation techniques. So we will use estimation methods to find the mathematical model of the system. One of the approaches that usually engineers are following is to estimate the constants Kd, Ks, and K using, for example, a least squares method. The basic idea is that we can place a sensor here. So for example, you can place a sensor, a distance sensor in this case, that will give you, let's say, a sensor. We can represent it like this, right? That will give you the displacement at, for example, time instant h, displacement of time instant 2h, displacement at 3h, etc., displacement until nh, where h is a small time constant, and having information about the force at discrete time instants etc. until we can form a least squares problem and we can estimate the constants Kd, Ks, and K. This is a basic estimation approach, and there are many methods used to estimate these constants using experimental data. So these are the experimental data. So the estimation method uses the experimental data collected by sensors to estimate the mathematical model of the system. One of the estimation methods is not actually estimating the precise values of the constants K, D, Ks, and K. Instead, this method will try to find a function, some kind of function, let's call it a g function, that will relate force at the time instant k. So let us explain this notation over here. Fk is a notation for f of kh. That is, it's a discrete time sample of your force. So this estimation method is trying to find the relation between the force at time instant k and the displacement at the next time instant k plus 1. So we are not interested in finding the precise values of these constants. All we are interested in is to find a mathematical relation in some basis that will, for known Fk, enable us to reproduce our displacement that will correspond to displacements of the true system. Generally speaking, the function relating the force and the displacement that we want to find will have the following form. So this function will have the following form. Now, what you can see over here are two nonlinear functions, in general case f and w. These nonlinear functions, let's for example, f has as its argument x and f. F is the force at time instant k, and what is xk? Well, xk is the state of your system. Xk is a state. In this video, I'm not going to explain what are the states of dynamical systems. You can Google it, you can find some secondary references. States are not purely mathematical objects. They have a deeper, I would dare to say even philosophical meaning. They have a deeper meaning. You will see later on the example of the mass and spring what are the states. So what we are having over here is equation saying if I know force at time instant k and if I know the system state at time instant k, I can predict the time instant can predict the state at time instant k plus 1 by simply propagating this function f. Now, if I know, the second equation tells us if I know the state at time instant k and if I know the external force at time instant k, I can compute my displacement. This second equation is called the output equation, and the first one is called the state. So the first equation is called the state equation, and the second equation is called the output equation. This equation basically describes the sensing process. So this equation tells you that you're basically measuring only the displacement. You're not measuring the velocity. And that's why it's called the output. Output is information that we extract from the system. Fk is an input from the system. So this mathematical model of the system has the following representation. So for known Fk, we can compute displacement at time instant k. That is, if we know the sequence, discrete time sequence of forces applied to the system, we can compute the prediction of the displacement of your system by simply propagating these equations. So let us now see how the state and the output equation look in the case of the mass and spring system. So this is our equation, an ordinary differential equation describing the motion of our system. Notice here that instead of k, I inserted c, since I want to distinguish between the discrete time instance k and this constant c. Now, the first step is to write this equation in state space form. So we need to introduce state space variables. We introduce a state space variable x1 as d and x2 as d dot. Now, if we take the first derivative of x1, we obtain d dot, and from this equation, this is equal to x2. So this is our first state equation. The second equation, the second state equation, is obtained by taking the first derivative of x dot. This is equal to d2 dots. And from the first equation, by substituting this equation into this equation, we obtain so these are two equations. This is the first one and this is the second one. These are two state equations. Now we can group them together in a vector, so we can write down zero, 1, so this is our first equation, and the second one is, let's see what happens here. So the second equation, x2 dot, can be written minus kd. This term here is nothing less than x2, right? Minus ks x1 plus cf. So our equation takes the following form. We are having here minus ks minus kd plus 0 cf. So this is our state equation. This is our state equation. Now, the output equation will be obtained by simply observing that using this sensor we are measuring the displacement. So our output equation will be d is equal to 1, 0 times x1 and x2. This is nothing less than the first equation. By grouping the entries and vectors, we obtain a nice system representation that you can see over here. So we obtain the following vector equation. This will be our state vector. X will be our state vector. And the first equation describes the state equation. The second equation describes the output equation. And these two equations, the state and the output equation, can be compactly written in this form, where A, B, and C are system matrices. So this is a standard state space representation of a linear system. Now, the main problem here is that our state space model is in a continuous time domain. And from the estimation perspective, or from the learning perspective, from machine learning's perspective, this is not convenient. So our next step is to represent such a state-space model in a discrete time domain. Now, there are several methods to discretize such a system. One of the basic methods is to use backward or forward Euler method. So if you use the forward Euler method, you can approximate the first derivative as follows. Now, the problem with such an approach is that this approach might lead to system instabilities. That is, although if your system is stable, this way of approximating the first derivative might lead to numerical instabilities and you will not be able to simulate such a system. Now, a better way, a more convenient and a stable way is to use the backward Euler method. So instead of using the forward differences, we use the backward differences and we represent the system dynamics, or actually the first derivative, as follows, where h is basically a discretization constant. And I'm going to repeat the notation. Xk denotes the state at the time instant hk. So if this is our state trajectory, we are looking at the state of the system at discrete time instant. So this is a discrete time instant k, and this is the discrete time instant k plus 1. This is time, this is the state where the distance between these discrete time instants is equal to k. Now, applying this approach to this equation, we obtain this equation. Now, we can manipulate this equation and then we can express xk, but just, for example, multiplying with xk. So what do we have here? We take xk on the left hand side, and on the right hand side we're going to have minus ha xk, and on the right hand side we are going to have xk minus 1 plus hbuk. Now, this equation can be written as follows. Identity minus ha x of k is equal to xk minus 1 plus hbuk. Assuming that this matrix is invertible, we can express xk as identity minus ha inverse xk minus 1 plus identity minus ha inverse multiplying hbuk. Now, this matrix over here will be our A discrete, and this matrix here will be our B discrete. So our system can be represented as AD x k minus 1 plus BD uk minus 1. Notice here that I have shifted the time instant for input uk, that is for our force. This has been done without loss of generality, just for simplicity. Okay, now this is our discrete time state equation, and the output equation in discrete time takes this form without any modification. So this is our discrete time system representation, and this system representation is convenient for defining the estimation problems. So here is our state space model. State at time instant k is a function of the state at time instant k minus 1, control input at the time instant k minus 1, this is our force, and the output is something what we measure is equal to C times, here I'm missing C, xk. So this is our state space model. Now, here comes the main part. So what you can see over here is a simple recurrent neural network. Now, notice similarities between your state space model and simple recurrent neural network. So what are the similarities? First of all, simple recurrent neural network is, similarly to a state space model, a recursive relation between this, I would dare to say, the states. So this qk and qk minus 1 in the neural network community are called hidden layer vectors. These are hidden layer vectors. However, don't they resemble the state of a dynamical system? In some sense, they resemble. Now, what is pk? Pk is the input vector at the time instant k. Okay, look here. Here's the input vector. So our input vector, if you want to train such a network, will correspond to the physical uk. That is, correspond to external force. Now, what is vk? Vk is the output vector of the neural network, and this output vector obviously corresponds to our output of our system. So the output vector will be the displacement. Okay, so we have hidden layer vector, state, input vector, control input, output vector, output of our system, and these parameters over here, they are matrices. This is a vector. These are matrices. They are parameters that we want to learn. So we want to learn to estimate them from the experimental data. And finally, these are the activation functions. Now, these are vector activation functions. Obviously, if these activation functions are identity, then we will obtain something that looks like our state space model. And if these terms here that are biases terms are 0, we will basically obtain our state. So here is our problem formulation. So basically, assuming that we have a mass in a spring system and assuming that we can observe y, or the displacement at the time instant 0, the y0, y1 is the displacement at time instant 1, y2 until, let's say, yn, and assuming that we have information about the force at time instant 0, force at time instant 1, 2, until force in time instant 10, our goal is to learn recurrent neural network models, not only simple recurrent neural network models. We will learn GRU and the long short-term memory networks, as you will see later. So we want to learn the parameters of such a network such that when we present to a network force F at time instant, let's say arbitrary time instant, let's call it I, our network should produce as accurately as possible the estimate of our displacement d at time instant I or at time instant I plus 1, that doesn't matter. Okay, so this is our goal. Our goal is to train the parameters to find these matrices. So we need to find these matrices, these parameters, such that when we present to such a network, that is, this will be equal to pi, so this will be pi, our network should produce vi, should produce the output. So force corresponds to the inputs of the network, and the displacement, or our yi corresponds to basically the outputs of the network. So this is our basic goal. We want to tune the parameters, to learn the parameters, to learn these matrices such that given a force at time instant I, our network should produce the displacement, a prediction of the displacement or an estimate of the displacement. And the network should be trained using sequence of observed outputs and input data. So, from the physical point of view, say that we have a mass spring damper system which can be represented as a block diagram. So this is our physical system. Input is the force, output is the displacement. Say that we actuate the system with a force that has the following shape in time. The output of the system will probably also have an oscillatory behavior depending on the damping and depending on other system properties. So this is your Y or displacement D. Okay. Now, say that we can collect so if this is our force, okay, say that we can collect discrete time samples of such a force. Okay, so this is our Fk and this is now K. And this is, let's say, time instant 5 and this is time instant 6. And say that we can collect displacement at time instance, discrete time instant. Again, this is, let's say, 5, this is 6. And this is Y of K, the displacement of K. Now, first, we need to determine the parameters of our neural network such that when we present, for example, this sample as an input to your neural network, let's call it F5 sample, your neural network should produce an estimate of the system output. So if this is the true value of the system output, that is the true value of displacement, your neural network should produce the estimates. That is, if we give as inputs to a neural network a series of forces, your neural network should produce series of displacements, such that these displacements, their graph approximates the graph of the exact value. So let's say this is the exact value. We should be happy if we obtain a response that looks like this, that approximates the true response of the system. Everything explained so far is summarized in the post whose link you can find in the description below. Here's the post. Here's our Statespace model, continuous time. Here's discrete time system representation. And here's our simple recurrent neural network. Here I explain the similarities and the difference between discrete time system and the neural network. Then in the post I start with a numerical example in Python codes which we are going to explain right now. So here's our spring mass damper system. We explained the Statespace model given by equation 5. This is the output equation. We explain how to discretize such a system to obtain equation 9. So equations 8 and 9 represent our system. Now, here's the Python code used to discretize such a system. I'm using NumPy libraries and I'm using matplotlib to plot the graphs. The system matrices are represented using this format. And to simulate the basic system response, I assume a random initial condition. I choose the time samples, total 300 for example, time samples, and I'm choosing the sampling constant or the H constant equal to 0.5. And this function here basically codes the backward Euler method for simulating the system. If I present to a system a step input force, the system response will have the following form. It will oscillate. So let us elaborate a little bit more on the system response and on the type of input force that will be used for machine learning. So if we have a spring mass damper system, and if you apply a force F that has, for example, time shape of a step signal. So step signal is a signal that after 0 assumes some constant value, for example 1. The output of the system, our output or the displacement of the system, as we can see from the graph over here, the system will oscillate, but it will settle after some time. So this is the output of the system in time. This is because we have a damper here, although the system is lightly damped. Now, this step signal is just used for first check of our discretization procedure to see, do we get something that's reasonable? And we're getting something that's reasonable. That's good. Now, for machine learning, it's not a good idea to choose such a force. In reality, what we can do, we can basically put a shaker here and we can shake. By some external actuator, we can shake our mass. So we can kind of tune our input force F. From the learning perspective or from the estimation perspective, it's better to have a force that's random in some sense, that randomly oscillates in time. Because this signal is richer in information compared to this signal. Furthermore, there is a condition called persistency of excitation condition, which I will not explain right now. This goes deeper into system identification theory. But this condition states that basically your force, or actually this condition requires that your force has certain shape, such that when you excite your system, so if you present a force F here and you collect the observation data, so if you have a random force, that your output is sufficiently rich such that you can uniquely recover most of the system parameters or most of the system modes. So this is a condition called persistency of excitation, and for machine learning, it's better to choose a signal that's random, an input signal that's random, or the force signal. So let us start with machine learning, with explaining the Keras library and explaining the basic procedure we used. Now, this code over here is used to define the system and to define the discretization constant and the time samples. Now, it's very important to emphasize here that we are using 3 data sets for machine learning. There are 3 data sets. The first data set, called the training data set, will consist of randomly generated input force and of the output of the system, that is the displacement of our mass spring system, obtained by simulating the system response for given force F. And here we will assume also random initial condition. The next step or the next data set is the validation data set. Again, for a random input force, we're going to simulate the system to obtain random system response. Here it's important to emphasize that this data set should be independent from this data set, should be statistically independent. So we generate one random vector and this is another random vector and they should be independent. Consequently, the outputs of the system will be independent. And again, we will generate an initial condition from which we simulate the system to be independent from the training initial condition. And we have the test data set. So the test data set will be used in the final stage of testing the model accuracy. Again, we are going to generate a random force and we are going to observe random system behavior by simulating the dynamics, and this will be done from a random initial condition. These two data sets will be actually used to choose the model parameters. So the training data set will be used to learn the model parameters, to learn the coefficients of our recurrent neural network. Validation data set will be used to select the best model, the model actually that gives the smallest validation error. This will be explained in the sequel. And the test set, data set, will be used in the final stage once we have selected the model to see how this model behaves on a data set, on a new data set that this model have never seen before, if I can say it like that. One of the most important and critical steps in training the neural network is to properly define the input and output data. So let us dedicate a few minutes to this important problem. Now, the TensorFlow and Keras libraries assume that inputs and outputs are organized as tensors. What is a tensor? Tensor is a fancy name for a matrix. So Keras library assumes that your input data is organized as a tensor having batch size times time, samples times the input features dimension. For the time being, we are going to assume a batch size of 1, and that simplifies our situation because we are going to have input matrices that will have time samples times input features. So your inputs for training the neural network will have the following shape. This will be time sample, and this will be input features. Now, to properly define this vector, let us look at the simplified model of a recursive or recurrent neural network. Qk is a vector of internal variables or your state vector. Pk is your input vector and Vk is your output vector. So what happens at time instant k1? You're having that q1 is equal activation function times, actually not times, that depends on, this means it depends on q0 p1. And output at time instant 1 is what? Is your beta, your activation function, times, or not times, basically activation function that depends on q0. 1 in this case. So what does this mean actually? Okay. So let's say at time instant 1, what happens? The internal output of your network will be represented by Q1. Okay, let's read this equation. We are having as an input state or hidden layer vector or state, however you want to call it, at time instant Q0. Then we are having an external input to your network at time instant 1. So we take P1 and we take Q0 and then we apply them to a function sigma to get the output. Not the output, again, you should be careful here, I should be careful. This is the state at time instant Q1. And we are getting the outputs at V1. Okay, so this output will actually implicitly depend, you see through this equation, will implicitly, this will be basically, if you just substitute this equation, this will be beta of sigma Q0 P1. So it will implicitly depend, V1 will implicitly depend on Q0 and P1. Okay, so this is how things are propagated. Similarly, at time instant, let's say this is 1, this is 2. Now, Q1 becomes an input from the left side. We are presenting P2, we are producing V2, and we are computing Q3 for the next time instant. And that's why it's called recurrent. So our inputs at every time instant should be presented to the network. And the output should be produced. So this is how the network works. And this dictates how the input data, these input tensors, will be organized. Now, this implies that our inputs to the network should be external forces acting to the mass and spring system. So we are going to have what? We are going to have what are going to be our internal, actually external inputs to the network. Here they are. Here they are. This is our input matrix or tensor. We are going to have U0, U1, U2 until, let's say, U199, since Python index uses indices that are starting from 0. Now, however, I'm going to have here two input features. Clearly, our input vector is one-dimensional, right? It's one-dimensional. This would imply that you only have to have input features equal to 1. However, be careful here. We need to provide an initial condition, our physical initial condition of our system at time instant 0. And this is the first state variable. This state variable in our mass and spring system corresponds to displacement at time instant 0, and x2 of 0 corresponds to first derivative of displacement. So we need to provide as an input to our network initial condition of our system. Probably there is a way not to do so. Probably there is a more elegant way to avoid doing so, because the problem is that in practice we often do not know the initial state of the system. However, for this video and for this implementation, we are going to assume that the input, actually the initial state, is known. and the remaining entries on the second column of your input tensor are going to be 0. So this is how our inputs for training the network will be organized. Similarly, our outputs are going to be defined. So the Keras and TensorFlow libraries are assuming again that outputs of the network for training are organized as three-dimensional matrices or tensors, where this will be the second dimension will correspond to time sample, and this third dimension will correspond to how many outputs at every time instant, let's say k, our network produces. In our case, this is equal to 1, since we are only measuring dk, the displacement. If you would measure two variables, here the dimension will be equal to 2, etc. And here this is a batch size. Now, what are the time samples? How the time samples are going to be organized? Again, not the time samples, this output data. This will be time samples, this dimension. And the first, actually the only column, will correspond to the outputs of the network. Now, remember how the inputs were organized. The inputs were organized like this. And these are zeros. This means that once we present an initial state to the network, our network should give us as the output what? It should give us nothing less than the first variable, the first state space variable. Once we present u0 as an input, the network should give us what? The network should give us y0. Present u1, we're going to get y1, etc. And we are going to end up with y199, corresponding to u199. Here you can also play a little bit. You can assume basically, you can shift the data. You can kind of shift the data that you don't get as the output initial state. You can basically shift this the up and down. For example, you can define this will correspond to y1, y2 until y, let's say 201. Depends what do you want to do. Do you want to have a predictor, or you want to have something that will produce the response of the system? Now our job is more or less done. Everything from now on is relatively simple for those of you who are familiar with Python. So what do? We create the training data. Here is the training data. Here is the code for defining the training data. So on this code line, we define a random input signal of the dimension time. Time is 200. And we define a random initial condition. Random position, random velocity for our state. Here we simulate the system to obtain basically the trajectory, the output trajectory or the displacement for a random input signal. And here we just organize the data. We reshape the data into the input-output data used for training. Then we generate the validation data. Here's the validation data. We basically repeat the procedure. We just generate another random input signal and another random state. And we repeat for the third time, we create the test data. So we have 3 data sets: training data, validation data, and the test data. Here we build the network. The networks, here are networks basically. We use basically, this is a standard Keras framework. We use sequential method. We use dense layers. We use GRU, gated recurrent units. Then we're using long short-term memory network, simple recurrent neural network. So we are going to test 3 different types of networks, and we import some solver parameters, and we also import model checkpoint, which will be used for saving the best model. Here we build the network. So we start with model sequential. These are the standard steps, and let's say we add a long short-term memory network. Okay, we organize the input shapes, the output shapes, and we add an output dense layers. This might not be necessary, however we are going to do so. And we basically compile the model. We compile the model. On the line 22, we defined a file path. We're going to use this file path to save our models during the optimization. And here we defined a checkpoint. This is very important. So we are saying here that we are going to monitor validation loss. Okay, so what is the validation and training loss? Let us explain this into more details. Now, during network training, let's say we have 2 data sets. We have the basically input training, and we have Y training. Okay, now in every training or epoch of training, if we present UT to the network should produce an estimate of YT. So the whole procedure of the training data is basically minimizing this difference in some suitable norm. Using some suitable norm, we can minimize mean square error or just a least square cost function, whatever it takes. So we want to find the parameters of a neural network. If you remember our neural network, we had this constant, we had these matrices L, W, the parameter Z, parameter G. So we are trying to find this parameter in every epoch. We're trying to tune them such that this difference is minimized. Now, and then at every minimization, we can define, and every step actually of training the network, we can define the training loss. So basically the training loss is the value basically of the difference between the data used for training and the prediction of the data used for training produced by the network, and this is called the training loss. Similarly, we have the validation data. So if we present the validation data to the network should produce validation output. That is the estimate or the predicted value of the validation. At the same time, we are having the true validation data that's obtained by simulating the system. And similarly to this cost function, we can define another cost function that basically is depending on the validation data. Notice that during the training is based on validation cost, and these parameters are computed. The training, actually the matrices that we want to learn, or the parameters that we want to train, are computed on the basis of the training data. However, once we have these parameters, we can plug them in a network, and for a given validation data, we can produce the validation prediction, and then we can go into the validation cost function to produce the validation loss. So in every epoch of training, we will have 2 losses. One loss will be training loss, another loss will be validation loss. And if these are epochs and these are J's, over time both curves should go down. At certain point, this validation curve usually starts to diverge from the training curve. So the validation loss starts to diverge. However, the training data will go down. So this phenomena, actually the point here, defines the best model. So our model will, the best model will always be defined on the basis of the validation loss. So the validation loss will be a measure of the quality of the model, since the training loss can be made to be basically arbitrarily small by keeping the by increasing the epochs. However, the validation loss at certain point will start to diverge. The training loss goes to zero since we are always minimizing. We're always trying to minimize this cost function. However, this cost function is computed for the values of the parameters obtained by minimizing the training validation, the training loss. So at certain point, we are going to have the optimal model. The optimal model is the model that produces basically the smallest validation loss. So in every epoch, in every iteration, we basically check how optimal is our model. And this is basically achieved by monitoring the validation loss. And in every time step, we are going to save. We're basically going to save the models. So we are going to obtain not a single model, but we are going to obtain, let's say, if we have 2000 epochs, we are going to have 2000 models for every point here. And then offline, once the optimization is done, we are going to just search for a model that produces the smallest validation loss, and this will be our best model. Finally, with this code line, we are going to call the optimizer. That is, we're going to feed the parameters. We provide as an input training inputs, training outputs, epoch number, batch size, and we also provide validation data. Okay, finally, once the optimization has been done, we are just going to load the best models, and we are going to, once for such a best model that's computed on the basis of the validation loss, we are going to do the prediction. Okay, so let us see how this whole procedure works in practice. So here is my Python environment. I'm using basically Spider. Why I'm using Spider? Spider editor, since Spider editor resembles MATLAB, and it's very easy to debug the code, etc. So here's the code. Here's the code. And I'm just going to execute until here. Okay. And I'm going to show you what happens when you basically, how the models are being saved online, etc. Now I'm just deleting models that are being used previously. Okay, now I'm going to execute code. I have to say that the codes are posted on GitHub and you can find them. Good. So this is how training works. You can see it over here. So epochs are the number of training basically sessions, or every iteration of the training process. Basically it's a parameter update. You can see what is being measured. Let us see what is being measured. It's a mean squared error, is basically value of your training mean squared error. Here you have validation loss, right? And you have validation mean squared error. At the same time you have loss. So these losses are more or less equal. This is the training loss and mean squared error. And this is basically validation loss and validation mean squared error. And you can see here, for example, that validation over here validation loss is smaller than validation, actually the training error is smaller than the validation error, or the training loss is smaller than the validation loss. And here you see how everything's being optimized. Here I'm just using the simple recursive neural network. You can also use GRU, LSTM, etc., depending on whatever you want to do. Okay, so I'm not going to wait until this is finished. I'm not using here parallel processing since I turn it off. You can also use parallel processing. You have a GPU and this will be done basically in 1 minute or more, depending on what kind of processor you're having. Now, once I'm done with training, I can plot the validation and training losses, and I can plot basically how well my network predicts the test data. You remember that I have the third data set, that's basically the test data set. So once I select the best model on the basis of validation loss, so how do I do that? Here you can see in the folder that every time instant or after some time my models are being saved. So I'm saving models on the hard disk on the basis of the validation loss. So this number, this weights 457. 457 is basically the epoch number, and this number 72.607, etc., is basically validation loss. So I will at the end select the model that has the smallest number. This, for example, in this case, this model will be 71.633, etc. So you can see how this is being updated. These are the saved models. So I'm going to have 4,000 models that will be saved. Now, I will load such a model over here, and at the end, once the model is being loaded, my weights will going to correspond to the best model. I'm going to use the test inputs corresponding on a test, corresponding to test data to generate the final prediction. And then I'm going to use this prediction, I'm going to compare this prediction with the true test data obtained by simulating the original system. And so what you can see over here are the results. So these are the results, the prediction performance. This is the real output. The real output is basically the output of the system, displacement of the system, displacement of mass and spring, and predicted output is basically prediction given by the neural network. Actually, these lines should be different colors, so the red color should correspond to real output, and the blue color should correspond to the predicted output by neural network. And this is basically for simple recursive neural network having 4 units. So what is the unit? The unit is nothing less than, if you see over here where you form the network, that's basically internal state dimension. Okay, and you can clearly see here as you increase the internal state dimension, or the number of hidden layers, right, in the networks, you're going to go from 4A to 32. You can see how the prediction performance improves. Now here there is one error here that I didn't notice by generating these graphs, is that I have set, in defining the network, you have an option here to set the bias. I didn't do that. So if you look at the code, I have corrected this later in the code. You can select here bias and activation function. You can select linear, non-linear. Here, to generate the graphs, you can see over here, I didn't do that. I just used the default parameters, so everything is being computed probably for non-linear activation functions and for the biases. That's why you need such a high model order, let's say 16, to obtain the results. And here you can see the training and validation loss. You can clearly see how the training and validation losses behave. Here you can see the prediction performance for the GRU network. Similar phenomena, you need a higher model order to produce the network output, although in practice remember that the state order of the mass and spring system is equal to 2, and here you have validation loss and training losses for the GRU, and everything is being done here repeated for LSTM. Now finally I have corrected what I made a mistake in my original implementation. So here I made a correction. I basically set bias to false, and I set the activation to linear, and I did that also to the output layer, and I obtained nice output results. You can see that the second order system, in this case only the second order system, even for linear simple RNN, is able to accurately fit your data. Okay, so as a conclusion, we have developed an approach for basically reproducing the input-output behavior of a dynamical system, basically using the recurrent neural networks. And we have demonstrated how to do that using Keras and TensorFlow libraries. Now, there are a lot of things here that need to be improved. The first thing that comes to my mind is basically that you cannot put in practice initial states and inputs, so they have to be a little bit formulated differently or completely avoided. So the idea is to try to generalize this approach to avoid the fact that you basically need to insert the initial states. Okay, and there are other things that need to be improved here, but I think that would be all for the time being. Thank you very much for your attention, and have a nice day.